Okay, we'll get started. So, in the first lecture, I'm just essentially going to revise algorithms you know, but it's also to sort of set terminology for how we will do this course, right? So, I'm going to talk about selection problems. What is a selection problem? Well, you have a list of numbers. Let's say numbers, it could be anything, list of elements where there is some order, and I want to find some element. Okay, so select some element. That's what my selection problem is. Okay, we are not just going to design algorithms, we also have to do analysis. That's going to be the core of the whole thing. So let me start with the simplest. I have this list of some elements, let's assume numbers, and I want to find the maximum in the list. Can somebody give me an algorithm for it? Wait, I want to see the sophomore person. Can you give? Sorry, what's your name? Aryan. Can you give me an algorithm? Given a list of n numbers, I want to find the maximum. Yeah, sit in. Yeah. So let's say it's given in some array, capital A. I keep saying numbers, but it could be set of some n elements where there is some notion of an order between any pair of elements. So it could be Mhm. So give me the program for hmm. Let's say I okay. Yeah, yeah. Go ahead. If AI hmm. What do you want to initiate with? Yeah. Let's say max. Max, what do you want to? Hmm. Int min. I don't know. I mean, you don't know what these numbers are. So, want to give minus infinity? Anybody else has any better idea? Yeah. So, what do I initialize max with? I don't want to deviate too much from. Yeah. Hmm? A of 0. Why not do that, right? Okay. So now I'll start from 1 and then hmm. Yeah, that's the entire program. At the end of it, you output max. Okay, so it's sort of a pseudocode, equal to arrow, whatever. I'm ignoring all the syntax here, whatever programming language. Okay, thank you. So that's an algorithm to find the maximum. So I'm just saying we care about time. How much time? How many comparisons does this algorithm take? N comparisons. Let's say. So by the way, if I'm going from 0, then it should be like 1 to n minus 1, right? Because let's say. So how many comparisons? N minus 1 comparison, because that's the number of times the loop is executed, right? So one question is, can you do better? This is always a question we will ask in algorithms. Can you think of an algorithm to find the maximum of a list of n numbers in something better than n minus 1 comparisons? So that's going to be better than n minus 1. So what he's saying is when you sort, it is there already. What do you need? What do you mean binary, sir? Why do you need binary? You sorted the last element. Okay. So, but sort takes some time. How much time will it take? Big O of? Sort takes big O of n? How many sorting algorithms? Is this better than n or less than n? N log n is much more. I mean, you obviously, you're doing much more than what I am asking. So, obviously, you will spend more time. So, that's not a better algorithm. Can you think of an algorithm which to find the maximum, but it will take less than n minus 1 comparison? This is a question you should be asking. I may not answer this, but right. But you had an answer? No. Somebody said some. I've overheard some answer, but any thoughts on this? Yeah. Can you find maximum using less than n minus 1 comparisons? Think about it. Okay, you can bring it up in the tutorial session. So now, suppose I say find second max, and this is what I mean by selection problem. I'm going to keep selecting something. Okay. So first, you hope you understand sorting is not a good idea because that's too much. It takes n log n time, and it is much more than what I really want. So why do all that? Right? Yeah. So suppose I want to find the second maximum. What do you think I can do? Exactly. So that's one idea, right? So keep two variables. What did we do before? We just kept one variable max, which at any point of time was the max. So if you have seen 10 elements, it shouldn't be hard for you to figure out that that's the max of that 10 elements you've seen so far. As we see new elements, we are updating it. So what she's saying is keep two elements, max 1 and max 2, let's say. How do you want to initiate? Yeah. So look at the first two elements, compare whichever is larger element, initialize max 1 to that and max 2 to the other element, and then your for loop will go as before, but from 2 to n minus 1. And what sort of comparisons will you do here? So now you have two variables, right? So this one will be replaced by, what do you do? If AI is greater than max 1, do something. Exactly. If AI is bigger than max 1, then this AI occupies the max 1 position and max 2 would move to max 1. Okay. So that's something you have to do. Otherwise, AI is not greater than max 1. Then what do you do? So you compare AI with max 2 and see if it is bigger or smaller, and depending on that you do some actions. Right? AI is less than or equal to max 1, but it's greater than max 2, then you do something. Okay, so that's algorithm. I'll let you complete the details here. Now let's count how many comparisons do you do. Let's be a little, yeah, carefully, yeah. 2 times. Two times n minus 2, because now the loop will go from there, plus 1 because the first comparison you make to figure out how to initialize. Okay, so it's roughly 2n comparisons, and there is a problem in the problem sheet about second max. How many people have seen this? No, because you don't know, you have to compare it with max 2, right? So I'm just testing how many of you actually have seen the problem sheet uploaded. So there is a problem about finding second max in the problem sheet. Anybody seen? No. Okay. Okay. So the problem asks you to improve this bound to something like n plus order log n. Okay. So this is, I think, the first problem in the problem sheet. Okay. Now, what has this got to do with the data science and deep learning and so on? Now, I told you it's a warm up, and this whole first week is about algorithms, analysis, randomization. You need to be able to appreciate these things, and that's why it's important to get your hands dirty on solving these problems. And these are like simple problems and puzzles. In some sense, these are puzzles, right? Think of it like a game. You want to find the second largest element from a list. How fast can you do it? Let's do one more. Suppose I want to find min and max. So what will you do? Okay, so you'll have two variables. Let's say min, max. What do you want to initialize to? First element. Now you say for I going from 1 to n minus 1, if ai, yeah, some answers from here. What do I do? Less than min. Okay, if ai is less than min, then min becomes a of I. Else, max becomes a of I. You don't know. ai is greater than min. That's all you know. How can you then conclude that it is the max? You have to compare ai with max. So you are remembering two things, min and max. Maybe this is 5 and this is 25. Some 7 comes. You are comparing with the min, and you find that this is bigger than this, but you still don't know. You can't say this is max. So you compare with max, and if so, if it's bigger, then you update your max to a. And you run through this. At the end of it, the min will have the min value and max will have the max value. How many comparisons have we spent? 2 times n minus 1. Right? One problem in the problem sheet asks you to improve it to 1.5 times n instead of 2n. Simple problems, it's like a puzzle. Think of it like a puzzle and solve them. And again, I want you, this gives you a flavor of how the course is going to be. Okay, algorithms, analysis, comparisons, we want to improve. I mean, this is one of the simplest. In the afternoon, you will be hit with randomization and probability, and then it gets hairy. Okay, so it's important for you to just get comfortable with these things. Okay, now, and then one can ask, let's say, finding kth smallest in general, right? This can go on. In particular, let's say some So, okay, let's see. So, what do you do? What's your guess? Yeah, so you can do this by keep some k values, right? K different variables, and when a new element comes, maybe you compare with one by one, and then figure out, you know, which one to throw away, and then keep going, right? So, roughly how many comparisons will it take? K times n. Can you think of slightly better way? Sort what? Sort the array and pick the kth, for example. So, this is like, how much time will this be? N log n. I hope you guys are following this. You know it's n log n. You understand this notation big O, because I mean, we could spend time on the tutorials, but if not, these are the things you should brush up and understand them. Otherwise, you know, you will be lost at least in the first week of the course. So, please make effort to understand them. But the thing is, I already told you this is not necessarily a good idea if k is small, right? So, if k is like 10, then what do you think? What would you do if I want the 10th smallest element? For example, if I want the 10th smallest element, can I do better than n log n? How much time will that be? Yeah, very good. So, this is a kind of handle I want you guys to have. Okay, everybody should catch up with this. Keep finding max. And delete. Okay, so I'm just writing like this, and this is going to take you. And when will the sorting algorithm be better than this? Not the size of the array. When k is large. When k grows bigger than log n, if I want, let's say, square root of nth element, this will be n times square root of n, but the other one would be n log n. So, if k is small, you want to apply this. But even instead of, so let's go back to this idea of I maintain some k guys. Okay, let's say I am writing this algorithm 3. Maintain k smallest elements. Okay, so at this point, whatever I have seen, I mean, initially I look at the first k elements, I sort them, right? Look at the first k elements. So, this is the smallest, k elements, whatever I have seen. My invariant I want to maintain, this is a very important thing for programming algorithms, is this notion of invariant. At any point of time in the algorithm, this invariant is maintained. Okay. So, what is the invariant I want to maintain? What I have here is the smallest k elements out of whatever I have seen. That is the invariant I want to maintain. So, now the new element comes, right, this ith element. I want to maintain this invariant. What should I do? What comparison should I do, and how do I maintain this? So, do comparison is a very safe answer. Of course, we are going to do comparison. Which comparison should I do? Max or min? Is that enough? Take the middle element and do what? So, what are you doing? Binary search. So let's say I count only comparisons, okay? There are other operations, let me ignore that. So what do? When a new element comes, I have to maintain this invariant that what is sitting here are the k smallest elements. It may not be true when the new element comes. So how do I maintain it? Well, first I go and insert this element into this list. Because this is sorted, I can do binary search, and then maybe this will get inserted somewhere here, this ith element, and it will push everybody, and maybe this thing will go out. In terms of comparisons, how many comparisons have I made? Log k. This is another important thing. Binary search takes log k comparison. I hope everybody knows binary search and knows that it takes log of the number of elements. So I'm spending log k comparisons at every iteration. So total time will be n log k. So plus k log k, right? Because initially I take the first k elements and I am sorting them. So this looks much better, much better than nk or even n log n. Because when k is n, this essentially degenerates to n log n. Right? This is actually better than both these algorithms. But there is something even better known. Okay, anybody knows one of the deep applications of divide and conquer algorithmic technique. Again, I'm sure many of you who have done a course on algorithms should have seen this, that you can find any kth smallest using divide and conquer. I leave it like this because this will take about at least half a lecture to explain how it works, but it's a very powerful application of divide and conquer. Okay, one of the things, at the end of an algorithms course, what is the cool thing you learned which is not otherwise obvious? I would say this is one such algorithm, that you can find any kth smallest element in linear time. So if you have seen it but forgotten, or if you have not seen it, please go and look up and find it. Right? There are several people who said they want to prepare for their placement interview. I mean, if I am sitting in the placement, I will ask this question, because this is telling you that I don't have to sort. You can do this was a big open problem in 70s. People were looking at, can you find, I just want this particular element, can I avoid sorting and do this? And this tells you that for any k, you want 100th element, root nth element, n by 2th element, you can find in linear time. Okay, so good. So now I'm going to just sort of switch gear and say, let's say I want to do these problems in this big data world. What is different? Why do I have to pay attention? What is different in the big data world, that even if I have to do the same algorithm, life is more complicated? Can somebody tell me why? So what are some of the challenges in this big data world? What is big data world? Well, data is coming huge, you can't even put them in your memory. There are other complications, right? So what are the complications? computation time. Yes, okay, that's also. So I'm going to say even n square is bad, right? If you've done a course on algorithms, we say that polynomial time is good, right? There is the notion of NP completeness. How many people have seen NP completeness? I'm not going to ask you, just seen. Okay, good. NP completeness tells you that there are a class of problems which are very difficult to solve, where difficult meaning that you can't solve in time, polynomial, you can't have an n power 10 algorithm, n cubed algorithm. There is no polynomial time algorithm. And polynomial time was sort of thought of as something you can do in practice. But in the big data world, even an n square algorithm is bad because, suppose n is like 10 power 10, then n square is 10 power 20. If your algorithm takes n square steps, that's like 10 power 20 steps. And your modern computer can perform something like 10 power 10 steps in 1 second. Let's say it's actually more like 10 power 8. Let's say you can do 10 power 10 steps in 1 second. Then how many seconds will you need to solve this? Okay, I was expecting somebody will say 2. People have said 2. So this is, maybe you have heard me before. This implies 10 power 10 seconds assuming 10 power 10 steps per second, and this 10 power 20 seconds is roughly how many days? You can check if you want to Google out and check. I think it's about 340 years. Okay. So n square is bad because n is large, but n log n is reasonable. Linear is okay. N log n is fine because if you do the same computation, n log n is 10 power 10 into log 10 power 10. What is log 10 power 10? So it's 10 power 10 into 10 into log 10. In computer science, logs are always base 2. So log 10 is, what is log 10 to the base 2? 3 point, right? Because log 8 is 3, log 16 is 4. So log 10 is something between 3 and 4. So this is roughly 10 power 10 into, even if I assume 4, this is the number of steps. In terms of seconds, this is 40 seconds. You just divide by 10 power 10. So there's a huge difference between 340 years and 40 seconds between an n square algorithm and an n log n algorithm. So one complication in the big data world is that even n square is bad. So you really want to do things in n log n or linear time. Okay, so this is okay. What else? What other constraints you think are we going to? Space. We have not done really, we didn't do any space analysis, but the point is, if you do merge sort or something, when you say, suppose I'm going to do sorting, right? Sorting, you can do n log n, merge sort is a good algorithm, but how much space do we need for merge sort? The last step of the divide and conquer thing, you have a list of size n by 2 and a list of size n by 2, each sorted, you're going to merge them typically you need an array of size like n by 2 to do this merging step. Okay, not always, there are more efficient, better algorithms, but a naive algorithm takes space. So, space is a huge issue. So, here for example, I would prefer log n or even better. Log n or log n kind of space. Third thing, important, the third step, that input model so for example, you have a large stream of elements coming, and they will come and go. You can't see them again. So sometimes, so for example, you are allowed only one pass over the input. So as it comes with this limited space, you need to store information about that, right? So that's another challenge. I'll give you, after the break, we'll get down to some specific examples and specific model issues. We'll see that something which we have seen, which seemed very obvious in the standard random access machine model we have seen, get more complicated when we restrict this model. Okay, so elements are coming, and as you come, you have this window where you need to store some in small space something about the input. The other thing is that we can't think of your elements in an array and modify move around. No, you can't touch it. That's a read only input array. You can only read it. If you want to do anything, use it in your additional space, which is limited. As you said, space is limited. It could be may need to solve in single pass. Or read only memory. So you cannot, like when you're doing insertion sort or something, you read it and then you modify the input. No, you can't do swaps and so on. You have to do everything in your additional space, which is limited. Okay. So these are some of the challenges in this big data world. So now we're going to go take a relook at some of these problems, like finding the median. Let's say, suppose the input is a read only memory. How do I do it? And you are allowed very small space. What can you do? Okay. So that's the kind of questions we're going to look at it, and that's why quickly we'll realize that in the worst case, there is nothing much we can do. We need to powerful uses of randomization is what helps us to save on space, particularly save on space in this restricted model. And so we are going to see a lot of probabilistic randomized computation examples, and we'll do slowly warm up and build towards it.